Welcome to the Microphysics talk. Here we'll cover the microphysics options in WRF, which are given by the MP Physics nameless choice. Microphysics interacts with other physics that we've already discussed. Cloud detrainment from a cumulus scheme, if you have one running, will provide fields for the microphysics. But microphysics can be run on its own without a cumulus scheme at high resolution and deals with all the cloud processes. It also provides clouds that the radiation needs and rainfall that goes to the surface. So the microphysics provides atmospheric heat and moisture tendencies, microphysical rates between species, and the surface resolved scale rainfall. In microphysics, we have to deal with any type of cloud that is resolved by the model. These clouds can be formed by radiative or dynamical or convective processes. This is an illustration of the cloud types that you can represent at high enough resolution. Models only consider the grid scale average, so it will not resolve the fine scale structures in these clouds. This schematic shows several examples of microphysics options in WRF with the species that are represented in these schemes. The simplest is the Kessler, which is called a warm rain scheme because it has no ice, and the only species it carries are water vapor, cloud water, and rainwater. This is really only useful for idealized cases. The next level of sophistication is WSM3, which has still 3 arrays, but now depending on the temperature, you have either ice or cloud water, or you have snow and rainwater occupying the same array. So there's immediate freezing or melting as the air goes through the 0-degree level. So there's some limitations on what these kinds of schemes can do with only 3 arrays, but it's mainly to save memory. Then the next level of sophistication is a 5-species array called, for example, WSM5, where the ice and cloud and rain and snow are now separate arrays, and so we have 5 total species, including the vapor and the interactions between them, as you can see with the arrows. And then the next level, which is more common, is the 6th level, 6-species versions of the microphysics. For example, linear tile WSM6, and they have graupel in addition to snow, which is more dense and falls more quickly, and is needed when you have high resolution. I'll go into all this more later. And a special case is Feria, which only has 2 advected arrays. One is the vapor itself, and the other is a total condensate with partitioning arrays to distinguish the different condensates. It's designed to be very efficient by only having 2 advected arrays. So this summarizes what I've just said. So we have these range of levels of sophistication. Warm rain, for example, the Kessler. Simple ice, still only 3 arrays like WSM3. Mesoscale, which is low resolution microphysics, where it doesn't have graupel and is sufficient for 10 or more kilometer grid sizes, WSM5. Then you have the single moment schemes like WSM6. I'll go into what double moment means later, but these contain graupel. Double moment schemes contain more arrays, including number concentrations, and then there's a further level of sophistication where they're predicting the shape and the density of the particles in some of our options. And then the final highest level of sophistication is the spectral bin options that actually resolve the size distribution. These 2 tables on this page and the next summarize all the microphysics options we have in WRF, which is quite a large number. Some of the popular ones are WSM6, Thomson, Morrison, and now the WDM6, which is a double moment version of WSM6. Then there's the NSL options. NSSL options continued here. WSM7 is a recent addition that separates the graupel and hail categories. Thomson has an aerosol option as well. And P3 is a newer type of scheme. I'll mention about that one later as well. And these are the bin models, options 30 and 32, spectral bin, microphysics, and I'll mention those later as well. Microphysics has to handle a lot of processes that also include latent heat release. For example, there's condensation, evaporation, deposition and sublimation, and freezing and melting that occur as particles change from one species to another. The particle types we're typically dealing with are cloud water, raindrops, ice, crystals, snow, graupel, hail. They're distinguished by size and density. The total mass of the microphysics does contribute to the dynamics, so there is a feedback to the dynamics through the liquid loading. The processes we're dealing with are aggregation, for example, from ice crystals to snow, accretion, as rain falls through cloud, it'll accrete some cloud and grow that way. Autoconversion, which is the growth of cloud water to rain droplets as the particles grow in size. Riming, which is a combination of water processes with ice particles, leading to denser particles. And sedimentation we have to deal with as well, and I'll talk about that later too, but basically some of these particles fall, and we have to treat that process inside the microphysics. In microphysics, you have to deal with how the particles are formed in various conditions. Cloud droplets, of course, form from condensation of vapor at water saturation. Cloud condensation nuclei can affect this, and some microphysics schemes allow those to vary depending on the pollution level, for example. Or chemistry can also provide the cloud condensation nuclei, but often it's a fixed number which allows for a condensation rate to a particular size of cloud droplets. Rain of the order of millimeter diameters forms from cloud droplet growth and also can grow by accreting clouds as it falls through. Ice crystals are tens of microns and form from freezing of droplets or deposition onto ice nuclei. So at cold enough temperatures at ice saturation, you can produce ice crystals from just deposition onto nuclei. Nuclei are assumed to be present always, but when you run chemistry, you can predict nuclei, which are basically dust particles. Snow, it's hundreds of micron size and forms from the growth of crystals at ice supersaturation and their aggregation. Graupel and hail are millimeters to centimeter size and form and grow from mixed phase interactions between water and ice particles. So snow and cloud water, for example, would merge to form graupel. And then denser versions of graupel, when there's more riming, more water, you get denser particles, which could be treated as hail. And precipitation particles are typically assigned to an observationally based size distribution. So these microphysics schemes have to make an assumption about the size distribution. The simplest size distribution is a log normal one in red here, where the number for a particular diameter goes exponentially with the diameter, and it decreases as the size gets larger, with an intercept at n0. The modification of that is a gamma distribution with a specified alpha exponent. So then you have d to the alpha multiplying the size distribution. And this allows it to go to 0 at the small end, whereas the log normal distribution had the maximum number of particles at the small end. So this is a little more realistic for some size distributions, and is commonly used also in the microphysics schemes. When you have mass of a particle that's easily related to the diameter, this is an example for water, for example, and then you have the force speed is also related to the diameter. It's usually a power of diameter. Then you can get lambda by integrating over the size distribution and relating the lambda to the actual total mass, and QR is the mixing ratio of rain, for example. So lambda, this gradient, is derived from the intercept parameter which is specified and the mass mixing ratio, which is a model variable. So the size distribution is completely defined once you know the mixing ratio. Similarly, you can do an integration to get a mass-weighted fall speed, which gives you actually this function, because the gamma distribution is very easy to integrate over size, and you can use various moments and integrate them along with the gamma distribution that just modify the exponent. So I mentioned single and double moment schemes, and this slide describes what that means. Single moment schemes have one prediction equation per species, basically the kilograms per kilogram mixing ratio, how much of that species there is per kilogram of dry air. So they're represented in the model by QR, QS, etc. And the particle size distribution is derived from fixed parameters, for example, this intercept parameter that I mentioned previously. For double moment schemes, you can add a prediction equation for the number of particles as well. So instead of a fixed intercept parameter, you can actually predict that. And so then you have the extra variables called NR, NS, etc. for each species. Double moment schemes may be either double moment for just a few species or all of the species, and there's a range of those in WRF. Having a double moment scheme allows for additional processes, such as size sorting during fallout. The size of the particles matters when the rain is evaporating, for example. And then aerosol effects, which affect the number of cloud particles, which then affects the formation rate of rain. So it allows for some additional sensitivities to things like pollution, for example, when you have a double moment cloud and CCN prediction as well. WRF also has a spectral bin type of scheme from the Hebrew University of Jerusalem in Israel, and there the size distribution is not assumed because you have one particle type for each size. So there's doubling mass bins, typically 32 doubling mass bins. So that adds obviously a large number of variables to a vect. And so this is an expensive scheme. It would normally not be used in any kind of forecast. It's mainly for research purposes. It's a way of getting closer to the truth in terms of less assumptions about sizes of particles and how they evolve. And so microphysics schemes, bulk schemes, which are the what I've been describing so far, can be tuned based on bin schemes, which may be closer to the truth by not making the size distribution assumptions. And in version 4.3 now we have a new fast bin scheme. These schemes have 4 particle types with 32 sizes, or 8, depending on whether it's the fast scheme or the full scheme. The full scheme, the added variables are different shapes of ice crystals. So microphysics particles, a lot of them have fall speeds associated with them. In fact, every particle I've described, except for cloud water, will have a fall speed. Rain, typical fall speeds are of the order 5 meters per second, and grapple or hail maybe 5 to 10 meters a second, snow 1 to 2 meters a second, ice crystals about half a meter a second. For long time steps, such as in mesoscale applications, and a fall speed of 5 meters per second, a raindrop may fall more than a grid level in a time step. For example, this would be 300 meters if you have a 60-second time step. And the lower level grids, they tend to be thinner than that. So it can fall more than 1 grid's level per time step, which would be unstable. So we have to do time splitting within the microphysics scheme to keep it stable. So the model will compute a shorter time step to do the fall speed calculations. and then apply that for the sedimentation terms. So many schemes use this time split method. Some schemes, the WSM and WDM schemes, use a Lagrangian method to also keep it stable. So the model does have ways of keeping the fall terms stable by either splitting or using the Lagrangian time step. So different species have different densities and shapes. Snow and grapple and hail, for example, are all ice particles, but they have different densities. And in reality, the density does evolve between them, and they're not so sharply discretized. So we have ways of trying to represent this. The simplest way is in the WSM and WDM6 schemes, where instead of having separate fall speeds for snow and grapple, there is a combined fall speed for snow and grapple, assuming that if you have snow and grapple in the same grid cell, there really are a merged particle type which has the characteristics of both, rather than having two separate discrete particle types that fall at different speeds. So we have a combined fall speed, which is just a weighted fall speed, applied to both snow and grapple. So that's one way to try and have a more gradual fall speed for the different particles. Other schemes can do this in a more sophisticated way. They can predict the density, for example, and allow the fall speed to vary gradually as the density changes. P3 also looks at the rhyming and the depositional growth, so it can compute kind of a density which will allow the particles to evolve naturally as opposed to through discrete stages. The Ishmael scheme also predicts density and aspect ratio and shape of particles. So that's even more sophisticated by actually predicting the shapes of especially the ice crystals. And the spectral bin scheme has separate ice crystal habits for plates, columns, and dendrites. So it has separate particles for different ice crystal shapes. The microphysics can interact with aerosols in various ways. If you're running WRF Chem can provide aerosols to some of the microphysics options, the Lin scheme, Morrison scheme, and the CSM, Mellerus, and Gettleman microphysics options. So there are some direct interactions between WRF Chem and some of the microphysics options. If you don't run WRF Chem, there are other ways of treating aerosols, especially by having a CCN as a predicted variable, where you can specify the initial CCN, the cloud condensation nuclei number, and that could be a function of pollution, for example. And then the microphysics can use that to produce condensation onto cloud droplets, and the sizes of the cloud droplets will depend on the CCN density concentration. So WDM, one of the NSSL options, spectral bin, have CCNs as a variable that you can initialize and advect, and then it'll affect the microphysics. Thomson has an aerosol aware scheme that has its own aerosols, the water and ice nuclei, which are initialized from a climatology and advected. Since version 4, it can also do dust emission with a dust model. So there are surface sources specified as part of this scheme as well, also based on the climatology. There's also a Morrison aerosol version that interacts with the climatological aerosols. There it's not advecting the aerosols, but it interacts with the climatological distribution of aerosols. Clouds also interact with the radiation, and the main thing the radiation needs from the microphysics is the sizes of the particles to do the interaction more accurately. So several schemes can pass their ice, snow, and cloud water particle sizes to the RTMG radiation option. Thomson, WSM, the WSM schemes, WDM schemes, NSSL two-moment schemes also all can do this. And this represents the so-called indirect on radiation due to drop size variation. So, for example, more polluted conditions lead to smaller cloud droplets which have a higher albedo, and that effect is represented when you know the particle sizes. Other schemes, apart from the ones I listed here, don't give the radiation the microphysical radii for the particles, so the radiation has to make its own assumptions about particle sizes. For example, its ice crystal size might depend on the temperature. This diagram summarizes the cloud aerosol radiation interaction. The microphysics passes the cloud amount and the radii to the radiation, which allows the radiation to produce the effect of those clouds more accurately. Aerosols can also come from chemistry and provide the water and ice nuclei for the microphysics to give the initial particle sizes. So there's an interaction between the chemistry and the microphysics there. Or you can specify the CCNs as an idealized constant value and provide them for the cloud condensation to the microphysics in some of the options that have CCN as a variable. Aerosols from the chemistry can also directly impact the aerosol optical depth that the radiation sees. So the radiation can see the chemistry aerosols as well via the optical depth that the chemistry will provide in the model. Note that sometimes these aerosols may not be the same as each other. The optical depth dataset may come from a different source than the aerosols that are going into the microphysics. So I've separated those here. In the case of WRF Chem, they are unified, and also in the case of the Thomson aerosol aware scheme, there is unification between how the aerosols affect the microphysics and the radiation. There's also unresolved cloud fractions to complete the picture here, which affect the radiation as well, not just the complete cloud cover from the microphysics, but also these cloud fractions. These tables summarize the schemes. It's 3 pages of tables. We have a lot of options, but what they show is the variables, the mass variables and the number variables, to give some idea of which schemes are single moment and which ones are double moment and which ones have even extra variables that they compute. So all of them will have cloud and rain and ice, and a lot of them have snow and grapple, and then some additionally have hail. And then the number concentrations also go with many of these, a subset or all of those species as well. These are some more schemes. Note that some of them have NN, which is a CCN number, in addition to the number concentrations of the particles themselves. And this one has a volume for grapple. And then you have the WSM7 has hail and grapple as separate species, as do a few others. And you have the Thomson aerosol, which has a few extra numbers related to the aerosols. The bin schemes, even though I've only listed these mass variables, it will combine its bins to these mass variables so that you can look at them in the traditional way with the QC, QR, QI, etc. But they actually can also output each size of particle. As I mentioned, it has maybe over 100 variables if you want to look at them all. But we do have this combined diagnostic output, which you can look at more easily. And also the numbers are similarly combined for the bin schemes. P3 has some additional variables listed below, as does Ishmael. And those are additional variables to help with predicting the shape and the sizes and the densities of the particles. So these are some recommendations for microphysics options. When you're at coarse grid sizes, you do not need a very sophisticated scheme, so you probably don't need a grapple scheme. Something like WSM5 would work, or even WSM3. for low resolutions if that's where you're staying. If you're doing nesting or anything down to high resolutions, you will need a grapple scheme, or at least grapple, and then some may want hail for some applications. In WRF, all the domains have to use the same microphysics options just to keep the same variables across nest boundaries. So whatever you choose for your inner domain in WRF, it'll actually force you to choose on all the other domains as well. But basically, when you're resolving updrafts, you do need grapple because you want the particles to fall out faster. If it was just snow, you get an unrealistic rainfall distribution and low intensity of rainfall that you don't really want. The primary rainfall output from WRF is divided into two parts. There's the one from the cumulus scheme and the one from the microphysics, if you're running both at the same time. So you'll always see at least these two rainfall totals if you're running both physics. The outputs are accumulations since the simulation start time in millimeters or kilograms per square meter. Rain C is the one that comes from the cumulus scheme, and rain NC is the one that comes from the microphysics scheme. That's convective and non-convective. The total is rain C plus rain NC. Despite the name, this is total surface precipitation, not just rain. You can partition it using the snow NC and even the grapple NC, which are the subsets of the total that come from the snow and grapple. So the rain then is the rain itself is then a subtraction of rain NC minus snow NC minus grapple NC. So it's not obvious because of the naming, but that name rain C and rain NC is the total. We also, as I mentioned earlier, have the bucket option for long simulations, which retains the accuracy when you're accumulating small numbers to large numbers. And we are advised to use the bucket MM option if you're running more than a month or a few months in a regional climate application. So this concludes the microphysics talk. We've summarized that the microphysics takes cloud from cumulus scheme, for example, and also can produce its own clouds through condensation and interaction of species. And then it'll actually provide the information, especially radius information for the radiation. And then also the microphysics provides a non-convective part of the rainfall to the surface.